Welcome back. Welcome to lecture 5 of week 5 on probability theory with actuarial applications. Today we are going to discuss one extremely important topic called extreme loss, okay, in which we will use one statistical concept called order statistics. I will introduce this concept to you and I will demonstrate how it can be effectively used in actuarial applications. That is the agenda for today. So, to set the context, let us understand why we need to model these extreme losses. Okay. So, when you are an insurer, you may not worry about your average loss that much, as much you worry about the extreme loss, that is either the minimum loss or the maximum loss that you incur, because that defines the range of your losses, and that range of losses can have significant impact on your portfolio. Therefore, you first let us look at both the extremes and then try to understand how these extremes affect us. For example, if you want to look at the smallest loss or the first failure, okay. So, if we have 100 wind turbines, when will the first failure occur? That is where we need to actually pay off something, right. So, what is the distribution of the time until that first one fails, right, and this particular thing comes as minimum of those random variables. All wind turbines are equivalent, therefore, and they are functioning independently unless there is some catastrophic event. All of them are functioning independently and we are simply waiting for the first failure to occur. So, what is the time that is required, because this time required will determine what insurance premium we set on the corresponding insurance policies, right. So, that is where we are interested in minimum of all of them. That means the first, whenever the first one fails, that will give me that minimum, right. So, what is the distribution of that? That is one thing, that is how we are interested in that lower extreme. Now, let us look at the higher extreme, where we are looking at the largest loss, and this is called catastrophic event, right. So, we have say 10,000 homes in Florida and we are interested in what is the distribution of the single largest hurricane claim, okay. So, over those 10,000, what will be the maximum claim that will come, okay. So, that is maximum of x1, x2 and so on up to x 10,000. This is what the reinsurer, the company which provides insurance to insurance companies, will worry about, right. So, how will you study all these things? One is minimum, another one is maximum. So, in statistics we give them a special name, we call them order statistics, okay. So, the study of first failure, second failure, third failure and whatever goes in the order relation, the random variables that are ordered, that study is called order statistics, okay. So, this we will study in today's class, okay. So, now that we have understood why do we need to study these extremes, let us design the theory behind it, behind this particular study. So, it is a theory of order statistics. Let us understand it from our probabilistic perspective that we have studied. So, one first thing that we will study is distribution of maximum, the extreme loss, okay, the max loss or the largest loss, right. So, if you look at our understanding from lecture 1, which is today this week's lecture 1, if I want to study yn, which is maximum of xi, so here it is very important to understand that it is coming from x1, x2 and so on up to xn. In statistics we call this as a population. This is a random sample from a population, okay. And now all these are, we typically assume all these are independent and identically distributed random variables, and then we give it this kind of notation IID with cumulative distribution function fx, okay. So, this is our understanding of this particular random variable. or this particular random sample from the population that we are studying. Okay. Now forget about statistical terminology. In probabilistic terms, what we are interested in is maximum of these x1, x2 and so on up to xn. This is what we are interested in. Do we have necessary equipment to study this? The answer is yes. I have that CDF technique, right? So that CDF technique can be easily deployed to study this. How? We will see now. So what is our goal? First of all, I need to find the distribution of yn, which is maximum of x1, x2, xn. I know the CDF technique. So what I will do? I will simply write f of yn y. What is it? Its probability of yn less than or equal to y. Then when you have this CDF technique, what you will do? You simply rewrite this as what is yn? Maximum of x1, x2, xn. So I have rewritten that as this. Okay. Now you think, if maximum of all these things is less than or equal to y, then what will be the x1? Will x1 be, can x1 be greater than y? No, x1 should not be greater than y. So x1 is less than or equal to y. x2, x2 should also be less than or equal to y. For that matter, if I take any xi, because maximum itself is less than or equal to y, all of these xi's should be less than or equal to y, right? And that logic continues till xn less than or equal to y, right? This is key driver of the fact that maximum less than or equal to y implies all individual random variables are less than or equal to y. If you understand this fact, then you are essentially saying that this everything or this probability is essentially equivalent to considering the joint probability like this. Okay. So this is our key insight. That means if the biggest one is less than or equal to y, then better all of them must be less than or equal to y, and that brings us into domain of joint distributions. So all of them is less than or equal to y. Now as I mentioned earlier, whenever we are studying such families, we take assumption of independent and identically distributed random variables. So here we will appeal the assumption of independence, and when I appeal to the assumption of independence, I can write this joint distribution into product of marginal distributions, correct? Because this is probability of intersection, which can be written as product of marginals. Okay. So I am very clear about this. That means what I am saying, Fyn of y is essentially equal to probability of these individual marginals less than or equal to y. Okay. But all of them are identically distributed. What is this? This I have already said that xi's follow fx, right? So if I say xi's follow fx, then this particular thing is fx1 of y or fx2 of y in our usual notation, and this is fxn of y. But all of them are mathematically identical functions. So I will suppress this x1, x2 and so on. If I suppress that, then I got this is nothing but fx of y raised to n, correct? So this is the insight. That means even without doing any other jugglery, just by visualizing an event in a proper manner, I am able to understand what is a cumulative distribution function of the independent and identically distributed random variables maximum. Okay. So this formula for CDF of maximum that we derived is Fyn of y equal to fxy raised to n. Okay. Now Here what we did, the biggest one is less than or equal to y, so all of them must be less than or equal to y. This was the insight that was at work. Now let us move on to the other extreme. Instead of having max distribution, what if I appeal to min distribution? Okay, will the insight minimum less than or equal to y work? No, the insight that will work is minimum greater than y. Minimum greater than y will definitely work. Why? Because if the minimum is greater than y, then all individual random variables must be greater than y. Have we studied such function? We have studied such function in exponential distribution when we were studying. So it is called survivor function. It is 1 minus survivor function in general is 1 minus f of y. Okay, you can easily see this is actually 1 minus probability of y less than or equal to y, which is 1 minus fy of y. So if I know survival function, can I determine the CDF? Yes, of course I can, right, because I have to use this transformation. That's all. So now we are basically we know what is a distribution. For example, if I take y1 to be minimum of xi's, then sy1 of y is probability of y1 greater than y, and then as usual I will replace this with the definition, which is minimum of xi. That is what I did here. And then what? Then this minimum will translate into probability of x, sorry, because it is y. So x1 greater than y, x2 greater than y, x3 greater than y, up to xn greater than y. Appeal to independence, you get this as probability of x1 greater than y into probability of x2 greater than y. Same logic, whatever I used in maximum case, same logic I am using. This, what is this? This, according to our notion, this is Sx of y. How many times it is covered? Raised to n times. Okay, so what I know, the survivor function is n Sxy raised to the power n. Okay, so that's the insight that we need to draw. Yes, so this is the key insight. Smallest one greater than y, all of them must be greater than y, and therefore if we use independence, it becomes product, and it is product of all these. So what is the formula? So formula is again easy. It's sy1 of y is Sxy raised to n, and what is Sxy? You can easily see this is 1 minus fx of y, the whole thing raised to n. Now we got CDF of minimum and maximum. Can we figure out what is the PDF? Of course we can, right? If it is a continuous random variable, we have mastered that skill in previous 2-3 lectures, how to find that. Just differentiate it and you get it, right? So now we have designed the necessary theory for handling extreme losses. Let us take application of this theory to some well-known distributions. First, we will look at minimum of exponentials. Okay, so this is an important shortcut, and it's in order statistics. It turns out that this is a very big shortcut. Okay, because exponentials are typically assigned to time to first failure, right? And you are talking about minimum of that. So that's why it has some special relevance. So let us look at the problem. I have a system of 10 independent components. The lifetime of each of the components are is denoted by xi, and I know it follows exponential distribution with parameter lambda equal to 0.1. Okay, y1 is the minimum time until failure, okay, until the first failure. So, it is basically minimum order statistics. And what is the distribution of y1? Can we compute that? Answer is of course yes. So, whenever I have this kind of setup, what I need to understand is what is this lambda. So, my density is f x x is lambda e raised to minus lambda x. Do I need to work with this? No. What I need, because it is a minimum, right. So, in the last slide we showed that survivor function is most important. So, s of x, what is s of x here? That is what we need to figure out. How will you find s of x? You will integrate from x, so because it is a dummy variable I will change it to t. You will integrate from x to infinity of dt, okay, lambda e raised to minus lambda t dt from x to infinity dt. You can easily see that this particular thing will turn out to be e raised to minus lambda x. It is very simple, you can easily see this particular thing happening. So, this is my survivor function, and it will become e raised to minus lambda x for all x greater than 0. Okay. Because you can also verify this, we have already done the necessary calculations. Sxx is 1 minus fxx, 1 minus fxx is 1 minus e raised to minus lambda x, and therefore sxx will be this. Perfect. If this is the case, then what I need to find is probability of y1, right. So, I want to find sy of y, right. What is the formula that we proposed in the last slide? It was sxy raised to n. So, I will simply apply that formula, which is sxy raised to n. What does this mean? This means e raised to minus lambda x, e raised to minus lambda y will be there, and this together to the power n. What does this mean? This is e raised to minus n lambda y, okay, and this is a survivor function. So, you can easily check CDF, fyy will be 1 minus e raised to minus n lambda y, and then you deploy this derivative tool dy of fy of y. This is our exercise from the previous version. So, it will become n lambda times e raised to minus n lambda y, sorry, y is in the power, for y greater than 0, and this is nothing but density, sorry, I will fyy, which is equal to this, okay. So, what is this? This, if you identify, because we also taught you one identification technique, recognize what is this density. So, it is lambda e raised to minus lambda, where lambda is replaced with n lambda. So, this is exponential with lambda equal to n lambda, parameter is n lambda, right. So, exponential n lambda distribution, that is the idea. So, what I derived just now is the distribution of y1 is exponential n lambda. So, let us go step by step in a systematic way, the steps involved. First, you identify what is a survivor function, because we know the survivor function shortcut. Put the value lambda to be equal to 0.01, okay. Then put the value n is equal to 10, okay. So, sxy raised to 10, just substitute everything, and what you got is e raised to minus y, and if you use this e raised to minus y, you already know this is nothing but survivor function of exponential with parameter 1, okay. What I showed you is the general rule which is mentioned here. If I want to take minimum of n IID exponential random variables, then the distribution that I get for y1 is exponential n lambda random variable. In this case, that n lambda turns out to be 1 for this particular problem. Great. So, we have understood how to apply this theory in minimum case. Let us take one more example which will handle the max case or the extreme loss, the other extreme. So, for that we have chosen uniform random variable. Okay. So, here we have to deploy this strategy using CDFs, right. So, I have 5 IID uniform 0 theta variables, and then we have to find the PDF of y5, which is maximum of x1, x2, x3, x4, x5. Okay. What will you do? First, do you know what is a CDF of uniform 0 theta random variable? Yes, I do know, and this I will denote by x, x following uniform 0 theta. So, naturally the density that I know is fxx will be 1 by theta, which is very clear for 0 less than x less than theta. Once I have done this, I need to integrate this. I will skip the integration, I will straight away write it will be x by theta for 0 less than x less than theta. It will be 1 for x greater than or equal to theta, and it will be 0 for x less than 0. Okay. So, this is going to be the CDF of this. What matters to me is this, correct. So, what matters to me is this. So, I will keep this in mind. Then we are looking at max. So, it relies on one logic. If I am looking at max, max less than or equal to y means all xi's must be less than or equal to y. So, with that logic, my fy of y is essentially turning out to be fx of y raised to n, correct. So, I will feed that in. That means all other things are 0 and 1. So, they do not change any, there is no change in that. So, x by theta will become x by theta raised to n for 0 less than x less than theta, right. Can I find the density of this? Yes, I can, right. So, I just deploy this method d dy of fy of y, which will give me, sorry, I committed one mistake here, argument is y. So, it will be y, this also should be y, correct. So, d dy of fy of y will be, because this 1 by theta raised to n is constant, d dy of y raised to n will be n y raised to n minus 1, correct, for 0 less than y less than theta. This is nothing but fy of y. Now, you push in all these values, n is equal to phi and theta is anyway theta here. So, n is equal to 5 you put, you will get the answer to be 5 y raised to 4 upon theta raised to 5 for 0 less than y less than theta is going to be my fy of y, and for safety I will write otherwise this is theta. Okay. So, I got fy of y, and let us see what system we have followed. First, you analyzed the CDF of uniform random variable. I have shown you how you have to integrate the PDF. So, you got this CDF. Second, you used that formula fxy raised to n, that after using that formula you got y raised to 5 by theta raised to n, very good. Then you differentiated this, you got after differentiating you got 5 y raised to 4 by theta raised to 5 for 0 less than y less than theta, and all others were constants. So, 0 otherwise. So, we got very important formula for this particular distribution. Okay. So, now let us try to focus on the strategy for finding the PDFs in general. So, we can get the general PDF formula by differentiating two main CDF or survivor results. In minimum case it was survivor function. Even if you differentiate that, that minus sign will be there, that will cancel itself off and you will get the PDF structure. So, why not have a general formula for designing these PDFs directly? So, here is the method, which essentially is equivalent to Jacobian method or chain rule in some sense for calculus. So, I have Fyn of y, I will differentiate dFyn of y, and that is derivative of this, and that gives me the density to be n fxy raised to n minus 1 fx of y. So, you can remember this formula. However, if you are conversant with calculus, there is no need to remember this formula, you just derive the CDF, differentiate it, you will get the answer. Okay. Next, for PDF of minimum of yn, you handle the survivors in a different way. So, this is 1 minus Sxy, and then you differentiate this and you got this Sxy raised to n minus 1 Sx dash y. So, it just but Sx dash y in itself contains one minus sign. So, that minus sign will cancel itself off, which is given here, right. So, this minus sign will come with this minus sign and therefore, it will cancel itself off and you get the formula in this form. Okay. If you want, you can memorize this formula. Otherwise, if you are comfortable with calculus, there is no need of memorizing this formula. Okay. These formulas are useful, but CDF survivor approach is usually safer conceptually. That is what I am always mentioning so far. So, this brings us to the end of week 5. Let us summarize what we have done in this lecture and then summarize what we have learnt in week 5. So, in this lecture we basically took two cases, both are extreme losses, one is max loss, another one is minimum loss. In max loss, we actually looked at the CDF approach and we gave a formulation in terms of CDF, which is Fyn of y is nothing but Fxy individual CDF raised to n. And in min loss case, we used the survivor approach, which essentially turns out to be Sy1 of y, y1 is the minimum of x1, x2, xn, and which is Sxy raised to n. We analyzed an important key shortcut. If I am dealing with exponential random variables, I do not have to do much. Minimum of n exponential random variables is again going to be exponential, and it will be exponential with parameter n lambda. Okay. So, this is what we dealt with in this particular class. In week 5, we have done significant progress. First, we started with CDF method in lecture 1. We showed that it is safe to work with this CDF method even if we use non-monotonic function. The isolation of x was the crucial step in this case. However, if I have monotonic functions, then I showed you a one-dimensional Jacobian method which will work very effectively, very fast. It is a 4-step algorithm which you can use and deploy for monotonic y is equal to gx. Then we expanded our scope and we handled the 2-dimensional world, where we learnt the Jacobian method in 2 dimensions. We learnt to handle u comma v, which are essentially functions of x comma y. So, here the key idea was I am projecting the xy plane into uv plane, and then I was trying to understand how the distribution will look like in uv plane. And then in lecture 3 itself, we integrated something out and we effectively figured out the sum, what will be sum of random variables. Then we took the same problem and derived a general method of convolution for independent random variables in lecture 4. However, in lecture 4 we noticed that if I am handling sum of two normal distributions and all other relevant cases, the integrals are becoming harder and harder. So we said that yes, so here is the time to think about some different method, and then we said in week 7 we will deal with this with moment generating function technique. So that is yet to come. Now in today's class we dealt with extreme losses, minimum or maximum loss. In such cases, if we are handling minimum, we have a survivor method. If we are handling maximum, we have a CDF approach. So we have lot of tools at our disposal. Okay. So this is how we are concluding week 5, and in the next week we will have some kind of power tools. One is called law of total expectation and another one is called law of total variance. These tools are significantly helpful when we are handling some of independent claims which are random in nature. Okay. So the claim number is random and the claim severity is random. Two kinds of uncertainties are there. In such cases, how to handle them, this will be dealt with in the next week, which is called law of total expectation and law of total variance. In this week, we will handle some complex models like compound Poisson, mixed Poisson. So I urge you to solve all the problems up to week 5 from the assignments and practice well the tools that we have learned, and then start listening to lectures of week 6. Okay. So see you in week 6 with more rigor and more passion. Thank you.